Welcome back, all of you, to the afternoon session of the fourth day of Faculty Development Program in Astronomy and Astrophysics. We have gone through a lot of sessions, and this session is also very interesting and it is quite relevant in the sense that galaxies are the building blocks of the universe, and how they evolve, what are they, and what are the different types, what are the morphologies. It's very important to understand all of them as a whole, to understand the working of the universe as a whole. So we have with us for this session Dr. Ravikumar, CD, who is the head of department, as well as associate professor in the Department of Physics, University of Calicut, and he is also the chief coordinator, CSS SEC University of Calicut. He is a member of the board of studies in the PG physics section. He is the director of the College Development Council since July 2nd, 2012 to, no, he was during that period, July 2nd, 2012 to January 17, 2013. And he was principal of CUIET during a phase in 2011 and 2012, and he is the in charge of Madhava Observatory at the University of Calicut from May 2006 onwards. He has done his PhD from Cochin University of Science and Technology, and postdoctoral research in Paris University, Paris in France, and his research interest includes structure, formation and evolution of galaxies, ultraluminous X-ray sources, active galactic nuclei, and stellar variability evolution. So we have a very eminent speaker, so I would request Professor Ravikumar to start his talk.
Just a second.
Yeah.
Let me start the presentation.
Yeah, it's visible. Perfect.
Yeah, I'm audible also, right?
Yeah, you're audible also. You're audible,
yes,
visible. Slides are also fine.
Yeah. I'm sorry. Today morning I had this throat infection, so I may.
You may go slow, no problem.
Yeah.
You may go slow. Yeah. You want water, you can take stop and take
water.
Yeah. Whatever you want to do.
Yes. Okay. So thank you, Jayan, for this generous introduction. I mean, I have forgotten many of these things. And thank you for giving me an opportunity to interact with this very diverse class of participants. I do research on the galaxy evolution as part of my PhD and later. Here, however, I am not going to discuss the detailed mathematical modeling or something related to complicated stuff. It's a fairly low-level introduction who anybody can understand. But if you feel any clarifications needed, you can ask by the end. And if I know the answer, I will definitely tell you. So, yeah. This is one line which I like very much. It was written by Jules Verne. Reality provides us with the facts so romantic that imagination itself could add nothing to them. See, many times what you feel when you do astronomy and astrophysics, it's a humbling experience. You might have seen the video where Carl Sagan requested and photo of Earth was shown like a blue pink dot, pale blue dot. It's like that. I mean, when you do the astronomy and astrophysics research in astronomy and astrophysics, you feel that the entire vast universe is so vast, even our imagination cannot go further, and we find that, I mean, that's beyond our imagination. And we see the irrelevance of mankind, even though, as of now, we know only the form of life that had we know we knew is on Earth. So here, doing astronomy and astrophysics in that sense is interesting. It's different from many other forms of science or even literature. It does not matter, research, because it has a lot from all branches. Astronomy and astrophysics means you are, for example, by definition of cosmology, the word cosmology is the study of the universe, and the universe means everything included. So it includes, in principle, all subject matter of knowledge that you can think of. And probably it started way before we started to read and write. So one of the examples for that is the Stonehenge, which is in the United Kingdom, in the UK. That is a structure like this with the big stones placed almost like a circle. If we know, it could be like this. I mean, this is a simulated structure. This is what is actually present. We really don't know what was it for, but all we know is that, I mean, the sunlight passes through the bigger inverted U, the window, and falls on different pillars on different times of an year. So it was most probably, because we don't know, the age that we calculate from the surroundings is that it's of the order of more than 5,000 years. So it's for our current knowledge, this is beyond our generation who started reading or writing languages. So, and this could be one of the first solar observatories. We really don't know the actual, because there are no other written or otherwise proof for that. So even though it is one of the oldest, on the other side of the story, we really don't know many of the scientific facts associated with the universe. We really don't know how, first of all, I mean, there is the Big Bang we call, but we really don't know what was there before. We have speculations, and we know that galaxies evolve, but we don't know precisely how galaxies evolve. So our knowledge-wise, it's actually a young subject. It is an old subject because it started early, but it's a young subject because we don't know much. We need to explore and find out more. But during the last decade, observation started dominating astronomy and astrophysics, so much so that we now can consider this as an experimental field without much loss of generality. For example, when we see in in the gravitational wave detection, you might have read the story about that, when two black holes or two neutron stars of considerable mass, when they merge. And it's as good as somebody sitting in Europe sits in his courtyard with a newspaper, and we read it from here. The technology involved is so complicated and so detailed that astronomy and astrophysics, the whole of this, has benefited from the technological advancement. However, we in this talk we will concentrate mostly on galaxies, and simply we will see what the classification scheme we have, the general properties of these galaxies, and then we digress in between slightly here and there, and we will try to understand the origin and evolution of galaxies. And to show at the end, we can see a few simulations of the formation and evolution of galaxies. So, first of all, the world of galaxies that we have, You must be, I mean, many of you, if you do professional or amateur astronomy, you must be knowing most of the stuff in the beginning. And hopefully, I mean, there will be something for you to get, okay? And this is something which I say, like, I should have, with an advertisement, every advertisement for free, for 5 rupees, so much, and they put a star, and they will say the star conditions apply. So this is my starred version. We are still to understand completely. I will be explaining things as if everything is settled and everything is clear. But remember, we are still learning a lot. The universe is so big and the phenomena are so complex that we always, I mean, the nature always surprises us with exceptions or special cases. Okay, so we will address, as we have seen in the title content page, the primary objective of this session is that to see where these galaxies form and where are they going and what will happen with that. Okay. So you all know what galaxies are. So it's basically collections of stars and gas, and it's bound by gravitation, and it is largest collections of mass we have. And typical mass is of the order of 10 raised to 11 solar mass. The mass of Sun is about 10 raised to 32 kilograms. And size is of the order of 15 kiloparsec to 2 megaparsec. 1 parsec is close to 3 into 10 raised to 13 kilometer. 10 raised to 13 kilometer is roughly 3 light years. Light years means the distance traveled by light in a year. So you know the speed of light. It is 300,000 meters, 3 lakh meters per second. And with that speed, if the light travels throughout an year, and that is the distance this much. So it's a pretty long, and that's the distance. And these KPCs are much bigger than that, and megaparsec of course. You may also know that the galaxies come in many different shapes. We have ellipticals, lenticulars, spirals, and there are barred galaxies, a structure in barred galaxies, and irregulars. So going by one, ellipticals, this is actually a spherical galaxy because it's actually a very big galaxy, and this is not actually smooth outer background galaxy. This is actually a jet coming out. Okay, but that's okay. That's from the optical picture, just like if we had observed Hubble when Hubble started observing in 1930s, 1938, 1939, he published The Realm of Nebulae, the book by where he described the morphology of galaxies. And when he took this picture in the optical band, okay, just like, I mean, it is similar to what we see. This is the picture. This is looking like a very nice galaxy. There are no structures. If you see the radio observation, this is completely a different story. But then there is something called isophores. Astronomers doing photometry are very much interested in that, and it's nothing but the line or contour, because basically even though a line here is actually a surface, because this galaxy is a two-dimensional projection of a three-dimensional object. So if I take the intensity, you know what isobars are, isotherms are, constant temperature region, constant temperature. Similarly, in the light, if you consider the photometry, the brightness, intensity, if you take the intensity and constant same intensity contours, okay, they are called iso. Yeah. I'm sorry. Isophores. Okay. So if you take the isophores of the galaxy, uh, they will be like ellipses. In the center region, you have maximum intensity, so there will be a small, close to circle ellipse. And as you go farther and farther, depending on the shape of the galaxy that you see, that can get more elongated or lesser elongated. Okay, and this is another elliptical galaxy. And elliptical galaxy, this is again a giant elliptical galaxy. You see other spiral galaxies, and this is the coma cluster where you see thousands of galaxies together. One of the properties about galaxies is that they come in all sizes. Okay, and this is also actually a much detailed photograph of the central region of an elliptical galaxy. To tell you that elliptical galaxies may not be always very smooth, even though Hubble considered them to be extremely simple systems at that time. Elliptical galaxies can be more complicated than they look like. I mean, it's a triaxial. Triaxial means it has different shapes from when you look from different directions. And the distances are so big. So for one galaxy, we have no way to go to another place and see its different orientations, because they are very far away and we cannot move that long out from the Earth. So we have to live with what our observations are. But even with that observation, we know that there are not only these three major axes different. In many cases, there could be what is called isoquattral twisting also. You can think of X inside it coaxially kept. You can think of it's slightly tilted from the main major axis. So if it is tilted, it will produce, instead of smooth isophores like ellipses one, you will see isoquattral twisting. You will see isophores bending. I mean, the ellipticity changing abruptly at different points as you go from the central region to the outer regions. So that means elliptical galaxies can be triaxial also. Their shapes, I mean, this is contrary to what we understood from, or what Hubble expected. Okay. And then there is the second class, lenticular galaxies. The lenticular galaxies, you see there is a bulge sitting near the center, a spheroid galaxy, and a circular, flat, thin disk of stars. If you slightly at an oriented angle, I mean, this is the angle of in the face of the galaxy. If you see it purely face on, you will see a circular galaxy because you see the circular disk. If it is slightly tilted, you see an elliptical galaxy. I mean, elliptical isophores. Okay, but this is not an elliptical galaxy. And you see here very fine lines of dust producing dust lines. And only with the help of Hubble's detailed photograph, you see this difference. Otherwise, if you had taken this picture with an ordinary telescope from Earth, this would be simply these details will not be seen, and you will clearly see a disk here. So this was classified lenticular basically because of that, and it is a lenticular. And this is another lenticular galaxy where you see the presence of a bar, a rectangular shape. I mean, it's not perfect rectangle, but it's not nothing else. Okay, it's a perfect. It's a rectangular bar-shaped region near the center of the galaxy. And this is a lenticular galaxy, and you have a. This is another very nice picture, which so happened to be that when we are observing it through the edge. The galaxy is like a flying saucer or a disk, and you see the close to the central region, and you see a lot of dust. If you had seen this from the face-on view, these disks are sitting as a thin cloud, and it is basically like our sun going behind the cloud. The cloud will be illuminated by sun, and you will see the patches of clouds. Similarly, there are stars sitting all around. Stars are in front and stars are in the back, but because they are sitting very close to the disk, the stars, we don't see the starlight along that direction. But if you happen to see from this direction, those lights will be very bright. This could be a very, very bright lenticular galaxy. So it's only because we are observing through this line. And this is again against Hubble's notion, because Hubble classified lenticular thinking that the dust, there is no dust, but actually there is dust, but the dust amount present in elliptical galaxies and lenticular galaxies is very, very low compared to a spiral galaxy, for example. When you look at this spiral galaxy, you again see the same spherical bulge at the center. A spherical bulge at the center, and again a circular flattened disk formed by the spiral arm. And the spiral arm is the disk is where you have more dust compared to an elliptical galaxy or a lenticular galaxy. And then there is, in addition to, it's a circular disk, but you see again orientation effects here, and the spiral arms. And spiral arms are where you have more amounts of dust. And to say you the same way, if you have more dust, you will have more star formation. So typical, our galaxy is a spiral galaxy. We find it's a few thousands of stars are born every year in our galaxy. While in an elliptical galaxy, it will be only one or two stars per year. So star formation is pretty large because you have more dust here, and more dust means less light. Okay, you have brighter stars sitting along the dust because of star formation scenarios that we have. Okay, another very beautiful. This is called, this kind of spiral galaxies are called succulent spiral galaxies, where the spiral arms are very clear. Okay, but you see there is another smaller satellite galaxy. This satellite galaxy will be soon captured by this bigger galaxy, and we will see some of the videos where this evolution is described. You see the next phase, actually it has started capturing. There in the previous picture it was pretty close to beginning, and now it has begun and it is started, because gravity is a long range force. You cannot say when it started precisely, because the gravity force always existed. But when you see this interaction, what happens is that the outer regions of this will be attracted by the outer regions here, and it will form a bridge or a tape, and then it will get distracted. I mean, if the galaxies are moving also, then this will be completely faster. We will see what is the difference of having an interaction and a merging, and what is meant by secular evolution, because they don't do any kind of interaction with any of these neighbors. This is another spiral galaxy now with a bar. Very beautiful, another spiral galaxy. You see the bar is structured here in the center, and this galaxy is a spiral galaxy which looks pretty close to our own galaxy. If we had an opportunity to watch like this, okay. So as I told you, what is the distance between this to this distance from ends of this galaxy? In our galaxy, it's a 10 raised to 11 stars, roughly, and it will take about 100,000 years for light to reach from this end to this end. It's a gigantic structure. And then we have obviously irregular galaxies, where galaxies without any particular shape, shapeless shapes or figureless figures. Many of the such galaxies are seen. It's actually irregularity is closely associated to interactions. Okay, uh, it also depends on a lot on where the galaxy is. We will see how the evolution and their position in the universe is linked. Sorry. Another set of these are ultra-luminous infrared galaxies. Okay, what do you mean by this? Ultra-luminous means, you know, luminous means bright. Ultra-luminous is extremely bright in infrared, and in infrared these are extremely bright. When you look for these extreme bright galaxies, what you see is you see different structures. They happen to be irregular, and they're most likely, okay, the explanation is that the galaxies or the part of galaxies that you are seeing are actually interacting with each other. And now what will happen when they interact, we will see in a while. So yeah, this is this is two jobs. Okay, this is a picture taken from the sky where there was only very few bright sources. This is actually, if you take the full moon in the night, you make it 100 pieces, 10 by 10, and you take one such piece, and that is the size of the sky. So we have taken a very small, very small place on the sky, used a Hubble Space Telescope because we have days and nights. Continuous observation is not possible, but Hubble Space Telescope, if it is placed properly, it can run long to produce continuous observation without falling behind the Earth's shadow. So if it's observing continuously for a very long time, this is what we call it. This is first of all surprising because we, with our own telescopes, we found that there are only a few, very few bright sources. All these dots, almost every dot you see here is a galaxy without any doubt. If you do photometry, stars are very bright sources, but compared to stars, how do you distinguish galaxies? Star galaxy separation itself is a very classic problem in astronomy and astrophysics. Now, for example, I mean this, okay, I know this is a galaxy because of the reason I told you, because this was taken from a place which is very close. As you go further and further, small dots, it will be difficult for you to digest whether, I mean, it's a galaxy or a star. There are different techniques, but what we expect is that in a galaxy, you see there are lots of stars, but but one star is situated very far away from another star. So compared to the size of the stars, the separation is very far. So when we place so many stars very far away, the stars are spread in such a way, filled in such a way that you don't see the difference between two stars. You see the galaxy as a continuous object. But even then, it is very far away if you take two stars. So when you take a picture of a star, it will be more or less a circular object. Okay, except for different telescopic aberrations. A very nice circular object, even if it is non-spherical. Okay, the star can be non-spherical also because of its rotation and other effects. But if you take a picture, because it is very far away, and what you are seeing is mostly like a circle. And then this all the objects which look like a circle, very point, very bright, you can classify like a star. And this is, if you apply that logic here, these 1, 2, 3, 4, 5. and obviously this one also. Okay, this is a star. This probably could be a star. Okay, but it is really not sure. But most of the object is a galaxy. And a galaxy, it is not like, I mean, this you see, look at this. This is, I hope it's clear in your screen also, like this. You can see the spiral arms. You can see the spiral arms here. You can see the spiral galaxy structure here. You can see much bigger, much better picture here and here. So they are galaxies like our own galaxy. Meaning light will take 100,000 years to reach from this side to this side. And this is a very, very small region in the sky. Now you think of that the sky is filled with these small pieces, and you calculate what could be the distance that we have. This is what I said. Our imagination will stop soon. We cannot think beyond. I mean, the universe is so vast. Okay, we literally know hundreds of thousands of galaxies in the universe that we can see, and we do believe that there is a visible limit for seeing distance, and there could possibly another island universes. Okay. But this, apart from whatever surprise I gave you, there was a lot more surprises in this when we observed these 5 stars-like objects. They are star-like, as I told you, those 5 bright blue dots. These colors are actually fake. Okay, don't get carried away by the colors. They are optical, but they are optical with 3 filters added together. So that, I mean, there is a special meaning for the color. Okay, you could, because I mean, you can give whatever color in image processing. So this was done in a particular way, so that, I mean, these 5 dots look bluer, and the other ones look somewhat yellowish. Okay, or red. And then all are star-like or photometrically. Yes, simple. If you ask without explaining that this was a very tiny region, very long exposure, etc., etc., you just show this to a photo. You just show this photo to an astronomer. He'll say, "Oh, these four or 5 points are definitely stars, and the rest are galaxies." But if you take spectra of these 5 dots, spectrum is something. You see, I mean, you get stars. Each star has its own spectrum, and galaxy spectra basically is collection of star spectra. So you are looking through a particular line of sight, and you see all the stars along that line of sight in the galaxy, in the farther galaxy, and then you take the cumulative effect of all the spectrum and all the spectra of stars inside. So here, if you look, it will be distinct from the spectrum will be showing different for a galaxy and a star, and it will be different. It is somewhat like our fingerprint. It will be different for different stars or different for different galaxies. We classify them depending on their similar common features. So if you look at this, they are actually at a very high redshift. Redshift means their distance that we estimate is very large. This is slightly surprising. These are very bright objects. If I have a 100-watt bulb and a 200-watt bulb, if I keep the 100-watt bulb closer and 200-watt bulb very far away, I will feel that this 100-watt bulb is brighter. Okay, which is quite natural. Now this is actually happening the other way around. We have a galaxy which contains large number of stars, looks faint. There is one object which looks like a star, which is very, very far away, and it is very bright. You understand? So it is actually brighter than the entire galaxy that you are seeing on the center. This center, this is the biggest galaxy in this lot. Even with that galaxy, you have these dots are much brighter than this galaxy. Because of this structure, we call them quasi-stellar objects. We were not clearly sure whether they were stars or a galaxy, so we call them quasi-stellar objects. We now know that they are called active galactic nuclei, the centers of big galaxies where supermassive black holes sit, and they produce very high brightness because of their accretion process in between their evolution. Okay, fine. But then, if you look at the spectrum of the five sources, all of them are having exactly same spectrum. This means that you are seeing one object in many different places. Those who do astronomy and astrophysics quickly understand that this is because of what is called gravitational lensing. It's a more picturesque way. You have a very distant quasi-stellar object with a host galaxy, but the host galaxy is very faint compared to. It's like if I place a lamp, a bulb, glowing lamp. If I try to take a picture of that, I will not be able to get the lamp post or things like that because they are very bright. The bright regions, you have to at the same time take the picture of the bright object and the faint object. If you concentrate on the faint object, your bright object will saturate, you will not be able to see the picture properly. If you concentrate on the bright object, you need very short exposure time, and so you will not be seeing the details of the faint one. So exactly like that. In the central region of the galaxy is so bright, you are taking a picture, you will see the central region, you will not be able to look for the details of the background. But those light coming from that star or star-like object, we call it quasar, bend differently because of the gravity, the cluster, the entire cluster, and you see it at different points. And this is what is the effect where you see different. All of them are same object at different places. Okay, let's go back to the world of galaxies again. So we have seen that, there are so many galaxies present, and Hubble with his humble effort, not first, but it is a gigantic effort. Okay, he classified galaxies into this tuning fork diagram, where in the handle of the tuning fork he kept elliptical galaxies, and he classed them like E0s to E7, depending on the ellipticity. E0 was circular, E7 was highly elliptical. And the disk lenticular galaxies were classified as SO. You write it as S0, but call as SOs. And then you have spiral galaxies, two types of spiral galaxies. One, the normal spirals, SA, SB, SC, and barred spirals sitting here. As you go farther in the arm, you see the bulge becomes smaller and smaller, and the spiral arms become bigger and bigger and clearer. Same here, you will have a bar in addition to that at the center. As you go farther and farther, the central region, the bulge part will become smaller and smaller, even the bar, and you will have the spiral arms clearer and clearer as you go farther. And you keep, Hubble kept irregulars outside this tuning fork diagram. So the $1 million question now we have to ask, what is and why do galaxies differ? Jayant, what is the time I have?
No, you have time up till 4:30. So as long as you want, yeah.
Okay. Oh, I will try to finish by 3:45 or so. Okay.
Okay.
Yeah. It's a as we have already seen, it is the study of how galaxies form and change over time. But what we can do, and we have to understand that, because can we study a galaxy evolving over time? We cannot observe an individual galaxy over evolving because the time scales are very different. Okay, our life is so short. But how do we do then? But in fact, because knowing the science behind, we can study different galaxies at different stages of evolution. We can see galaxies evolving by observing different galaxies classes. I can give you this example. The bees live short, a few weeks on. If bees had intelligence and they wanted to study humans, because within few days, unless we get a disease or something, we don't change much, right? So how do they study humans? They could have taken the entire sample they could get, like 1,000 people from a village, and they will see, they will classify people, say, in the form of length and weight. Then they will see that, length, there are very small length, very big length, long people and short people. They will classify that short people are probably the younger ones, long people are older ones. Here, in fact, just like our HR diagram in the star, this will give you an idea about where people live longer. Okay, in the which phase. As you see, I don't have a plot here. You can think of that the number of children will be less and their height will be low, and the number of people that you get with a low height will be much smaller. Number of people in the bigger height will be more. So if you draw a length weight against weight, it will be very similar to the HR diagram. You will see different patches, filled differently in the diagram, showing that people are evolving more and stable when their height becomes somewhat high. Okay, because by 20 we know people don't grow far in their height. So this is interesting. So what we do? We just take whatever we have. Whatever galaxy you take a photograph, you study, and then club together all the properties and see whether there is any. So that is what. Okay. But there is one more interesting feature because of exploration of science we got. Oh my God. So. What we can do, I said, is that we can see the history of evolution of galaxies. How? For that we need to understand basically two things. That's first thing is the universe is expanding, and second thing is the velocity of light is a constant. I will explain each one of these slightly again. Velocity of light is a constant. Does not need any kind of explanation, because in vacuum the speed of light is a constant. So if it is far away, it will take long time to reach you. So clubbing these two means the farther the galaxy, the younger it appears. So what do you mean by expansion of universe? The universe is expanding means the famous balloon analogy. It is, you look at the dots, okay, the crossing each other, okay, at the dots here, dot here, dot here. As you blow the balloon, these dots become farther and farther. So distance between one dot and all other dots increase. The distances increases as you go, as you blow bigger and bigger. So in the context, what does it mean? Does it mean that the distance between you and me is increasing? No. Does it mean that distance between you, our Earth, and Moon is increasing? No. Distance between Earth and Sun? No. It is not even the nearest galaxy we have is other than our galaxy is the Andromeda. In fact, Andromeda galaxy is coming towards us. So if you take farther galaxies as a dot, all the galaxies are running away from us, not closer galaxies. Those galaxies which are pretty close to each other may interact and merge. Or interaction means it will be glazing, merge means it is completely colliding each other and destroying each other depending on the size, angular momentum, etc. So each dot, I mean each galaxy is running away from each other if you consider all farther galaxies. And they are actually, Hubble's famous observation is that they are not only running fast, they are actually running faster if it is farther. This is more complicated, which is not needed now for us. Think of in an accelerated motion, when a ball is falling down, the speed, because it is accelerated, the speed each second it travels more distance as you comes down and down. So the velocity increases as it comes down. This is accelerated motion. Exactly like this. Now think of the scenario is different. You think, I mean, the galaxies are running away. You can think in the boundary there is a big wall which attracts all these galaxies. So from here, all galaxies are running faster and faster as you go farther and farther. So now let us take the picture here. This is since the light is running with a constant speed. Think of two galaxies. Okay, one is this is our galaxy Milky Way. Sorry, this is the nearby Andromeda galaxy. Say, okay. In Andromeda galaxy, there happens to be a supernova explosion where its brightness increases very fast. But we will not see it now. 400 million years ago, light will take 400 million years to reach us. By that time, this galaxy has reached here. Our galaxy has reached here. Now, when you see this, you are seeing, there is a sudden supernova burst. But that had happened 400 light years away, 400 million years back. So, what you see in the whole universe is not the picture that is existing now. It has existed before. For example, our sun emits light and it reaches around 8.5 minutes. So we will do similar 8 minutes to reach here, say. So if all of a sudden for some reason sun is stopping its production of light, imagine. We will not see it now, we will not realize it now, we will see it only after 8 minutes. So we are seeing light left 8 minutes back. The nearest star we have is Proxima Centauri, it is 4 light years away. So we are seeing 4 years back of that state. If that star, Proxima Centauri, exploded and vanished, we will realize it only after 4 years. So now the story is simple. You take galaxies, all galaxies in a distance ladder, and then classify as part of their distance. When you see galaxies which are very far away, they must be at a younger age. Galaxies close to you will be at a older age or more evolved. So evolution now you can study by taking the galaxies in a long way, along the distance. Now if I am not putting the slides, I mean I will put every knowledge into one slide. Okay, these are actually in the blue. What you see is properties of galaxies placed from clusters. So if you take brighter galaxies become in general are older ones because they are also bigger also. Brighter galaxies are rotating faster also. The rotation is slightly different. Okay, it is not rotation with a in all cases like an axis. For example, in the case of spiral galaxies, there is a rotation. There is a symmetric rotation because you have a rotational axis which is perpendicular to the plane of the disk, and the stars are moving in a circular motion. But in the case of elliptical galaxies, the motion is completely complex because one star will be moving like this, say considering the central supermassive black hole as the central mass. Another star will be moving like this, and there will be, it is a three-dimensional close knit motion, but they are, stable in the sense, the collision probabilities are less, but there is no common axis of rotation in the case of elliptical galaxies. But if you have methods to gauge that also, then you find that the effects of rotation is more in bigger galaxies. An intense emission line, when you see very bright lines, very bright galaxies, they are almost always strongly interacting. Finally, bigger and brighter galaxies show higher entropy. Meaning, entropy means if you have a process, entropy is basically an idea about the quality of disorder, okay? The amount of disorder present. If it is the more disorder, you call the higher the entropy is, in simpler terms. Now, when I say brighter and bigger galaxies, if I take smaller galaxies and bigger galaxies, small galaxies show small entropy, big galaxies show big entropy. And in thermodynamics, there is a fundamental rule that in all reactions, entropy will always increase. There is no way you can bring back the entropy down. So, brighter galaxies have more entropy means it is telling you the way galaxies evolve. You can start with the smaller ones, you can go bigger and bigger. If the entropy moved the other way around, you could have said, oh, the other way have. So it is now, our belief is that galaxies can form smaller and make it big. And now if you take in a cluster environment, you take all galaxies together in a small region, then you find that ellipticals and lenticular galaxies are very abundant near the center of the cluster. You remember in our first picture where we showed elliptical galaxies, there was a giant elliptical at the center in the coma cluster, and the outskirts you see lesser number of ellipticals, galaxies. Our own galaxy is a spiral galaxy, and we are not part of the central region of our own galaxy cluster. So, compared to many spiral galaxies, our spiral galaxy is actually an above average sized galaxy. So you see that ellipticals and lenticular galaxies are abundant near the center. Spiral galaxies are abundant on the contrary in the outskirts. We call it field regions. Okay. It is as you go farther and farther from the center of a galaxy cluster, you see more and more spirals. This is called density morphology relation or density radius relation. This has a famous discussion, which is more fundamental. Okay, the number density you consider, number density and the radial distance from the cluster. Number density or the morphology relation. Okay, both are in a way the same, but there are slight differences because you can take a cluster environment. You can take another environment where it need not be a fully grown cluster, and then again, will you see such a relation where you have more density? Will you see more ellipticals and ellipses. But so far, so good. We now understand that the environment, where the galaxy originated, has certain role in its evolution. So environment and evolution of galaxies are closely related. So now let us theorize two kinds of formation. You have a galaxy. How do we get a galaxy? As I told you, we need to have stars. We need to have stars. From where do you get stars? We will get stars from clouds. So you imagine a gigantic cloud, then you will have stars forming from the clouds. These stars evolve and become finally a large number of stars are there. That will be a galaxy. So the typical galaxy, like dwarf elliptical galaxy, will have 10⁶ stars. Our own galaxy, as we have seen, is a 10⁻11 stars. The giant elliptical galaxy will have 10⁻13 stars. So you imagine such that, I mean, it is a bigger cloud, you will end up with a bigger galaxy. There is no collision, no interaction, no exchange. It is evolving isolated. This is called secular evolution. On the contrary, you can see, imagine a hierarchical merging scenario where galaxies start smaller, they merge to become bigger galaxies. Those bigger galaxies will merge again to become more bigger ones, and it goes on like. So this is this is what we have explained so far. Galaxies evolve independently, no interactions with others. Gas is converted into stars, and stars evolve and die. And finally, all stars are exhausted. Okay, you call it the end of the galaxy life. On the other side, galaxies start small, increase their size, mass, brightness. So what is the difference between hierarchical merging and the galaxy, the secular evolution? In secular evolution, the total mass is more or less conserved. So you don't increase the mass, you don't increase the brightness drastically because you have to form star one by one. But what happens when there is a merging? You see, we have seen the picture of an elliptical galaxy where there is a thin dust line, a disk of dust. So this is what is going to happen when two galaxies collide. In fact, as I told you, Andromeda galaxy is coming closer to us. In another 200 million years, it will collide with our own galaxy. When it collides, what will happen? If we had seen that, it would have been a beautiful moment. You know why? Because, as I told you, stars will, I hope you can see my hands. You can imagine that stars are situated in the tips of my fingers. This is Andromeda, this is our galaxy. When they come closer and closer, will there be collisions between the stars in Andromeda and stars in our own galaxy? The probability is very low. This is a beautiful thing. You see, as I told you, the size of a star compared to the distance between two adjacent stars is very, very small. It's like two people standing and firing on in the sky. Okay, what is the probability of two bullets, one bullet from one person and the second bullet from the second person collide? Because compared to the distance, you have to be extra smart and extremely sharp to get to point to one point and say, it is colliding. So exactly like that, even though there are 10⁻11 stars in each of these galaxies, Andromeda is slightly bigger. Okay. The collisions, except for the very central region, there won't be much of the stars colliding. But we have the dust sitting. The dust of this galaxy, it is like this. I mean, it is not like this. Okay, it is, the dust is situated closer. They come and hit each other. When they come and hit each other, dust will condense. Dust will have more dust together in smaller space, and that is ideal for more new stars. So that is what is happening. When it collides, you will start. I mean, it will not collide completely hot. It will simply collide and pass through. Stars will pass through. Dust colliding at central regions will form a star, and some of the rest will move somewhat here. When they come back again, collide, and this will do a few times. The stars will move in and out. The dust will move lesser, but each time they will produce more and more stars. So this starlight will be coming more and more all of a sudden. So merging causes not only increase in the brightness, not only increase in the shape, change, everything changes fast in the case of merging scenario. Okay, the picture it is not showing, it is showing only the shapes are to solve. It is not like that, it is just a cartoon. Okay, so merging gives you an idea about stellar galaxy evolution, because in a secular evolution we can understand that the evolution takes very, very, very slow. Okay, good. What is the proof that galaxies interact? These are all actual pictures. Okay, there is no simulation yet. You see these, the spiral structures being, this is a picture from Earth. You see another picture by Hubble Space Telescope. Now we will be seeing most of the pictures from Hubble. The nuclei, these two bright spots are actually nuclei of two different galaxies some time back. They collided and they are getting destroyed. I mean, finally, normally what happens is that when two spiral galaxies collide, we will end up forming an elliptical galaxy. And most likely in our own simulations show that with the Andromeda galaxy merging with our own galaxy, the end product will be a spiral elliptical galaxy. See here, galaxy interaction produces big tails running across megaparsec length, because the size of the galaxy is kiloparsec, so this is of the order of megaparsecs. Intergalactic distance is of the order of megaparsecs. Another Eagle's Eye galaxy. Okay, you see this Eye is actually another spiral galaxy. You are seeing it at a slightly tilted angle. This had gone through one set of interaction. It is going again, because you see that the interstructure of the bigger galaxy is already disrupted, because that most likely this could have come here and now it's going back. Oh, this is another picture where we saw where instead of galaxy, I mean, if you take pictures of galaxies, you see a large number of interacting as you go farther and farther. I mean, smaller sources, you see more and more interaction much. Here, on the other hand, this picture was taken basically to show you that in the earlier case, you had gravitational lensing producing fine dots. Here, you see fine arcs are formed by gravitational lensing, because you are not observing a point source in the background, you are looking at another galaxy. Another galaxy is in the background of this galaxy cluster, and you see that light. So if you had taken spectra of these arcs, they will show all same redshift of a galaxy which is not seen actually by you, by us. It is in the background of this galaxy, the galaxy cluster. So the story, the universe had a more violent history when it was young. This is also true to understand that we are seeing the universe is expanding, meaning distance between two galaxies was small when we started small, when the universe was younger. It is expanding means the distance between two galaxies is becoming farther and farther. So when the size of the galaxy is comparable to the distance between them, interactions are more plausible. If the size of the galaxy is much smaller compared to the distances, then interactions will be less possible. So because of this, in the universe was small, you expect more collisions in the past. So again, another picture. I mean, how do you know that this galaxy is not in the background and this galaxy is in the foreground? Because of this. When they come together, they will disrupt each other's. In fact, the disk itself is a very unstable structure. Okay, because that can be destroyed by supernova emissions inside the disk. It is definitely destroyed by collisions. So they are not. I mean, when you see the spiral arms, it is actually telling you the other way that I mean it is more recent interactions. The proof that though that galaxy had gone through an interaction in the past. Okay, and if the interaction was strong, that disk would have lost. So it's a existence of disk is an idea giving us that that galaxy has passed through a kind of interaction in the back. Oh, this is another very beautiful picture. It looks two different galaxies, but you know, if you study the properties of the stars, this shell, okay, is actually stars left or stars captured by this big galaxy from this one. It had passed through. It has passed through from this that day, and it is now coming back. It will finally merge together and become a bigger galaxy. Another three galaxies colliding. This is called the mice galaxy. There are galaxies falling. I mean, we will see a couple of pictures, simulation showing the different nature, from one galaxy, when two disk galaxies merging. In a simulation, we will show these effects in a while. The pictures are much larger. What do we expect when galaxies merge? As I told you, when the galaxies interact, they come close by, and there may be a small tail forming, and the galaxies will go far away. So they will not disturb each other. That is called a minor interaction. In a major interaction or a merging, this is not the case. They come, there is a strong gravitational coupling between them, that some part of the material is attracted by the other one, and there is a bridging occurs. Once the bridging has occurred and the collision is going on, it is going like this and this way, and the total disruption of the system, and depending on the final equation, you can get big galaxies, and they will definitely merge together and form. I mean, you can get spiral galaxies also depending on the dynamics. If you have a big spiral galaxy and a smaller spiral galaxy, then the end product will be still a bigger one. So here, in the pre-merging scenario, there is first one is the tail formation. Second is the coalescence, nuclear coalescence, the two nuclei of the first galaxies. Okay, they collide, and then post mergers you see, as you go with the time, you see definite shape that lasts slightly longer. Okay.
From where you are giving the meeting?
So let us look at the simulation. You start with the small dust clumps.
Can you do
now these are small galaxies, and they come, collide, become bigger and bigger. The central regions, you see, all around they are. Okay, you can take spiral arm.
You can hear from the
again. These galaxies are small now.
So you don't read mic.
You see that continuous. I mean, like this is actually interesting. If somebody had asked, how do these galaxies start rotating?
It will be taken by camera.
We started with linear momentum only.
Very comfortable.
So it's a
Okay. You tell the boy, he will arrange it.
more and more collisions, and finally the mass
You tell him.
is sufficiently large to
He,
attract the
he
rest of
knows
the
better
matter
than
around.
us. He knows it.
And you see there is a small satellite galaxy that is coming back. It is not directly colliding. Now it will come and it will go back and come back and collide. You see,
No,
it
no,
is not a
6:45. You
direct
tell me.
collision. It is going
Any
by,
problem, you call me.
yeah. And there is a bar formed in
Okay, that I
between
will see
in
after.
the process.
Not that 6:45. We will see afterwards. Can keep it.
You see, the small satellite galaxy went without harming the gigantic spiral structure. So this is actually, the simulation is running pretty fast. It is gigantic structures that take very long time to produce. You see this? It has passed through major part, but some part was attracted by this galaxy. And it goes on, you get the spiral structure. Now if you had a big spiral galaxy colliding with another big spiral galaxy, we will see in a while. Okay, let us finish this. This is the formation of a spiral galaxy by collisions with the smaller and smaller amounts of dwarf galaxies. Say. Okay, so what about the next? Now, if you take two spiral galaxies, okay, their inclination is slightly different, so that this is an actual observation. Now they are coming closer and closer. This is the simulation part. They come and they start colliding. And if you had actually seen this from this way, it would look like another galaxy, which I showed you, the mice galaxy in the first. Now again, it's going on. The nuclei are separate. I mean, it's actually very far away in this particular line of sight. You see, the picture is like this. The nuclei is coming closer. There is the bridging is already there, and this is another real picture of a galaxy. The simulation continues. This is available in YouTube. It's not mine. You see the disturbed shape. Oh. So, I mean, the idea is not to do one simulation and match with all. It so happened that, I mean, all those simulations, I mean, could be matched with some of the observations. So we didn't talk much about dark matter, dark energy, etc., angular momentum feedback, Gantt log, etc. But the overall picture is this. I am coming to the close of my talk. It's a 1 second. It's going like this. This is the age of the universe. You know, we are around 13.1 billion years old with our current estimate. And when the universe was small, you get smaller and smaller galaxies, and they evolve, they merge. You can get young galaxies up to 3 million years. Beyond that, they could collide. If they collide, you end up with the bigger galaxies, and if they also collide, you will end up spiral galaxies. If the spiral galaxies collide, you get an elliptical galaxy, and if the smaller ones again collide, you get a dwarf ellipticals, and they collide together, you end up with a big spiral galaxy, a big elliptical galaxy. If so happens that, I mean, there is after a few initial collisions, they happen to be in a region where further collisions are not possible, they end up as irregulars even today. So this is the whole picture that we try to understand in the universe, how galaxies evolve. So in summary, galaxies form the fundamental building blocks of the universe. In the early universe, galaxies experienced a lot more interactions than today. A combination of secular evolution and hierarchical merging scenario is needed to explain the observed properties of galaxies. And thank you.
Yeah, now now this session is open for discussion. If anybody have any questions, they can ask the speaker directly by unmuting themselves, or they can put in the chat. Any type of questions or discussion?
Yeah, I have a question. A very good afternoon.
Yeah, please.
Yeah, first of all, the talk was very nice and interactive regarding to the galaxies, the form basic to the and current scenario of galaxies in our universe. Yeah, I have a questions to Professor Ravikumar that what are the effect of dark matter and dark energy in the current scenario to the perspective of the galaxies or merging of binary?
Oh, yeah. That's actually a good question which I did not mention because of the associated time constraints with that. I hope everybody knows what dark matter and dark energy are. I mean, I was pretty close. We have said that galaxies are running away from each other. So it is like a wall situated outside where the galaxies are attracted. So they are accelerated. Exactly on the other side, you can imagine this that there is a repulsion between two galaxies. And because of the repulsion, a repulsive force is higher if the galaxy is farther. So this kind of fictitious repulsion is dark energy, where dark energy causes galaxies run away faster. On the other hand, dark matter is something which we really don't know again, but its presence is felt gravitationally. So, and gravitationally meaning it is most likely it is not a clump, it is spread across the intergalactic space, and it provides the channel for formation of galaxies. So near the centers, its dark matter is again gravitationally attracting, dark energy is gravitationally repelling. So dark matter is needed for us for many reasons. So you could have asked, dark matter channels, it decides the potential where matter will flow and finally form into galaxies. While dark energy is a repelling force, it is what we say it is for the explaining the expansion of the universe. Dark matter, on the other hand, there are people who think dark matter is not essential because we are not observing it directly. There are many observations which demand the presence of dark matter. One of them is actually our gravitational lensing. You could do the calculation of mass, how much mass is needed for gravitationally bend light from a background object, like in the quasar. So if you calculate the mass needed using Einstein's equation, then you find that the mass needed is much larger than the visible matter that we have. There is another rotational motion of stars within a galaxy also hinted that we need more dark matter at the center. So our scenario is that dark matter is possible to support formation of formation of galaxies at a particular point because of the potential decided by the dark matter. But dark energy is something which destroys galaxy formation. Okay, it is throwing away galaxies. I hope I clarified that.
Yes, sir. Yes, sir. Thank you. Thank you so much, sir.
There is a question from Preetam Singh. She says that how can we understand the morphology of the galaxies and we can determine the radial velocity?
Okay. Morphology. Okay. The morphology is what you see from the optical picture. You have to be very, very careful. Okay. This is, we can think of our own picture in infrared. If we had taken infrared picture, infrared is sensitive to light, and light will be, our whole body will have almost same temperature. Heat is radiated through our the nostril, mouth, eyes, and ears, slight amounts. So it will be more bright if we had taken, and it will be completely different. So it is interesting for you to look at the picture of an animal in infrared and in ordinary light. Exactly like that, if you look the same galaxy in different wavelengths, its picture will be completely different. For morphological analysis, we are using optical analysis only. So what you get is the morphology. What you get is actually the projected effect. Okay, you are not seeing like this. You can see it's like this. So you really don't know what is actually it is curved or not. So we are seeing a three-dimensional objects, two-dimensional projection on the sky. So that we get directly. Now, how do we measure radial velocity? Radial velocity is measured using a redshift. Redshift, I hope you know, the Doppler shift. As an object moves away from us, its frequency received by us will be extended. Wavelength increases. The observed wavelength increases compared to the emitted wavelength. Or if it is coming together, you can see that the reverse happens. So by measuring the wavelength change or the change in the wavelength, you will be able to measure the redshift, and using that redshift, we know how fast the galaxy is running away.
Okay. Any other questions from anybody else? Okay. So if there is no more questions, I would like to thank Professor Ravikumar for having come here and delivered the talk in such details. In spite of his having health issues today morning, he said that his throat is not okay. So I said you manage somehow slowly as far as possible. So anyway, he obliged and he came. So I thank him so much for coming here and delivering in the platform and delivering the talk. And if you have any other questions also, you can post it always in the this our WhatsApp group, and it will be answered by the professor. So thank you so much.
Thank you very much.
Sir.
It's always nice to see you, Jayant, and all my dear friends. Thank you.
Thank you.